KP was that while you were doing KP in AS, what you had to do was you had to find partial pressure. So I'll just give you one. I'll just do one question on KPK. What happened in KP was it was the exact same question as KC. For example, there was 2 moles of. अच्छा मैं आप लोगों ने mute all कर रहा हूँ एक second अपना. अच्छा so KP was a chat एक second on करने दो. अच्छा so you have a question on KP. You've got let's say 2 moles of N2 and 3 moles of H2 are mixed together. Gas, okay, they're all gases are mixed. Together. At equilibrium, once equilibrium is reached, so at equilibrium, uh, 1 point, maybe value 1.82 moles of N2 is present. And they told us the total pressure at equilibrium. The total pressure of the container is 2 atmospheres. ठीक है, इसके फौरन बाद we'll start with A-levels equilibria as well. Achha, so you've got this question. The equation that you have is that there is क्या equation होती थी? N2 gas plus you've got 3H2 gas, and on the other side you have N2 gas plus 3H2 gas. On the other side you have 2NH3 gas. Your initial moles, TK, your initial moles, TK, I'm just writing I over here. The initial moles that are given, that's 2 moles. And H2 moles, that's 3 moles. And there is no ammonia added, so that's 0 moles. Okay, there is no ammonia added. And the equilibrium moles are given as well. The equilibrium moles, in the question they've told us that's once equilibrium is reached, 1.82 moles of N2 is present. So what is happening is that you had 2 moles of N2 initially, and now you have 1.82. That means 2 minus 1.82, what is that? That's I guess that's 0.18. So that means 0.18 moles got used up, they reacted. You get minus हो गया. So 0.18 moles are reacting. So if 0.18 moles are reacting, it's 1:3, which means that if one reacts, so how much H2 would react? That's going to be 3 moles. So if 0.18 moles are missing, that means they reacted. So what amount of H2 would be reacting with it? So that's going to be, because it's 1:3 in the reaction. So यहाँ पे it's going to be 0.18 times 3, which is क्या value बनती है 0.18 times 3? That's calculator एक second निकाले 0.18 times 3 कितना हो गया? That's 0.18 star 3, that's 0.54. So that means 0.54 moles of H2 must have reacted with it. And if one reacts, on the other side, double would be produced, right? So 2 of them would be produced. If 0.18 are reacting, that means on the other side, double the amount would be produced, and that's going to be 0.18 double. That's 18 plus 18 कितना हो गया? That's 36. And that's the amount that's going to be produced. So your equilibrium moles would be that you started off with 3 moles of H2 and now 0.54 have reacted. So you're left with 2.46 moles. ठीक है, माइनस हो गया. You start off with 0 moles of NH3 and 0.36 got produced, so your net amount of moles is 0.36. ठीक है, so you found your equilibrium moles. अब इसके बाद ये बताना है कि I mean the next thing that you're going to talk about is since you've you've found the equilibrium moles. ठीक है, you've found your equilibrium moles 1.82, 2.46 and 0.36. Now what is happening is all these moles combined at equilibrium, all of them, they are exerting a pressure of 2 atmosphere. Remember, we are supposed to calculate Kp. So all of them together, they're exerting a pressure of 2 atmosphere. Now the expression for Kp is pretty simple. It's partial pressure of the products, which is NH3 in this case, and that's going to be squared and divided by the partial pressure of N2 times the partial pressure of H2, and that's going to be cubed. Okay, so you have to find the partial pressures. So how do you find the partial pressure of, let's say, N2? That is the moles of N2, which are what? That's 1.82 divided by the total moles, which are, I mean, total karna padega. What is the total moles? That's 1.82. Let me add all of them up. Okay, so it's 1.82 plus 2.46 plus 0.36. And that gives me 4.64 moles times the total pressure, which is 2 atmospheres. I'm going to find the partial pressure of H2, which is what? It's the H2 moles are 2.46. So it's 2.46 divided by the total moles, which are coming out to be 4.64 times 2 atmospheres. And I'm going to find the partial pressure of the last one, which is ammonia. That's so the partial pressure of ammonia would be 2.46 divided by what? 4.64 times 2 atmosphere. Okay, so in Kp, you just have to, if you remember Kp in S, all you had to do was you had to do this extra step, which is that you had to find the partial pressures. Okay, it was the fractional percentage. Okay, remember, is jagah pe you can also have fractional percentage over here. It's the moles of the gas divided by the total moles, or if they give you the percentage, whatever the percentage is, you're going to use that percentage multiplied by the total pressure. So anyways, you're going to plug all of these things into your expression over here. Okay, all of these are going to go over there. So it's going to be a lengthy calculation, and let's try and do that quickly. Okay, 1.82. I'm going to try and do that quickly. 1.82. Just 1 second. Let me. As I said, it's 1.82 divided by 4.64. Okay, times 2. And that gives me times 2.784. So N2 is 0.784 times, I'm going to do H2 now. So H2 is 2.46 and divide that by 4.64. And then it's going to be times 2. And that's giving me 1.060. And that's getting cubed. And you have your numerator, which is NH3. That's let's say NH3 मैंने गलत लिखा, but this is not 2.46. This is actually 0.36. Okay, that's what NH3 is. And 0.36 इसको कर लेते हैं 0.36 and divided by 4.64 and times 2, and that gives me 0.155. how are you? 155 rounded to three significant figures, and that's going to be squared. So my final answer would be 0.155, and that's getting squared. Okay, that is squared. So that's getting squared. And then it's getting divided by 0.784. Okay, and then it's again getting divided by 1.06, and that's getting cubed. Okay, so I'm getting 0.0257. I mean, you would have to double check this. I don't have a calculator right now, but that's what I'm getting. So that is what KP is. ठीक है अच्छा आप सारे वो चार्ट कर सकते you can just write yes or no over there. अच्छा now so that is what KP is and that's AS. ठीक है, this is all equilibria for AS. We would soon start with A levels as well. So just remember KP is that is exactly the same as KC. You have your initial moles, you have your equilibrium moles, you try and figure out based on the amounts that are given, you try and figure out what your equilibrium moles are, and then you plug those moles, not those moles, but the partial pressure, that's the extra step that needs to be calculated. And that is then added to your expression, which is this one. Achha, moving on, what we're going to do is what we're going to do is we're going to start with A levels chemical equilibrium. So now this is, remember your KC and KP concepts. A levels chemical equilibrium is mostly what you, it's just application of KC and KP. Now, we know any equilibrium constant is basically what? It's the product concentration or pressure divided by the reactant concentration or pressure. Now, the very first equilibrium constant, remember, it's just an application. It's the same exact concept. We're just going to start applying the same concept to different scenarios. So the first one that we're going to do is that's known as the ionic product of water. Okay, that's the first equilibrium constant, and that is known as Kw. You can remember we're applying the same concept, but to a certain situation. The ionic product of water, and that's Kw. This is also known as the water constant. And keep this in mind that all equilibrium constants are constants until you change temperature. So, so always remember that equilibrium constants, they vary with temperature. Okay, they no longer remain a constant if you change temperature. So as long as the temperature is fixed, the constant is going to remain a constant. You can keep this in mind. AS maybe pada, you already did this. They only change with temperature. Achha, so what is the ionic product of water? What that is, it's basically and achha, water is something that's very, very important because water is everywhere. All chemical reactions, especially on planet Earth, you see any two particles. Achha, if you see any two particles, chemistry is all about collisions. It's about two particles interacting, maybe losing electrons, gaining electrons to each other, or sharing electrons, right? But those particles don't exist in a vacuum. Most of the time, those particles are, so most of the time, those particles are floating in water. Because the human body, 70% of it is just water, your blood is water. So water is kind of everywhere. And all these particles, they're floating around. They're all floating around in water. Okay? So if you didn't have water, the particles would never be able to collide with each other. Okay? So plants can be all the movement of particles happens because they're floating in water in your cells, in your blood, in your own body, all the particles are moving around. And the reason they're moving around is, and the reason they're able to interact with other particles and collide with other particles is they're floating in water, right? So water is something that's very, very important. Now, the thing with water is, if water tends to ionize, okay, there's a simpler equation which you already know, that water molecules are going to bump into each other and the water is going to break down into H plus 1 and OHs. Okay, so water ionizes and it ionizes very weakly. Like water mostly doesn't do this. Like you've got thousands of molecules, maybe one or two might ionize or break down. So there is very weak ionization. But this equation over here, this is not the actual equation. This is not the true representation of what's going on. What actually is going on is that if you see two water molecules bumping into each other, this thing that we call H plus 1 aqueous, it in reality does not really exist. What actually exists is that if you see two water molecules bumping into each other, water is a highly polar molecule. The H is strongly positive. The water molecule has lone pairs, which are highly negative. So what happens is that one of the H gets attracted to the lone pair of the other water molecule, and that H goes and sticks to the other water molecule. So this is what in reality happens. A dative bond is formed. So if I pick this one up and I paste it here, so what's going to happen is that this positive H is going to be pulled by the other water molecule and its lone pair. And this H plus 1 would go and it would eventually form a dative bond. It's going to get attracted. Remember, it's plus 1. Okay, because it lost its electrons over here, which is why this OH would be negatively charged. Okay, so the H over here left its electrons over there and got attracted to the electrons of the other water molecule. And the other water molecule is capable of forming a dative coordinate bond. Why is it capable? Because it's got an extra pair of lone pairs, which this H plus 1 can easily borrow. Okay, so this is the actual reaction that's taking place. So basically, it's not H plus 1 because remember H plus 1 cannot survive in water alone. The H plus 1 quickly binds with the other water molecule. So when you say H plus 1, what you actually mean is an ion which is known as the hydronium ion, that's known as the HCO plus 1 ion. Here the reality is this is the thing that is produced. That's the molecule that is actually produced. And this is the actual equation, the action that's happening. But both of these equations, this is the simplified equation, the first one that we wrote down, that water ionizes and produces H plus 1 and OH ion. And this over here is the slightly more complex equation, which is kind of the same. But this is the one that's the thing that's actually happening. So this is the true representation. I'm gonna write this down. So actual And this one is, the first one is the simplified reaction, okay, which you've been studying all along. So keep this in mind that even in your A levels, H plus 1 aqueous and the other one, which is HCO plus 1 aqueous, they kind of mean the same thing. Okay, they kind of mean exactly the same thing. So ये वाली बात clear है? Is this thing clear? हालत clear है? तो वैसा सना मैंने, is this clear? Over clear है?
Yes.
Yes, sir.
ठीक है. So, अच्छा, but the important thing is that keep this in mind, that this thing called H plus 1 aqueous and this thing called HCO plus 1 aqueous, they're actually the same thing. Okay. So you can use both equations. It's up to you. You might see both equations in the questions. In one question, they might use the second equation. Another question, they might use the first equation. But apart from that, what do we do with these equations? Well, both of these equations are reversible reactions, which means that they are in equilibrium. They ionize and they also form the water molecule back again. So they're at equilibrium. And since they are at equilibrium, they're going to have an equilibrium constant. So the equilibrium constant would be, if for either one of them, the equilibrium constant is product concentration divided by the reactant concentration. So if I use this equation, the one that's in front of you, so it's H3O plus 1 concentration times your OHN concentration divided by the water concentration, and there are two water molecules, so you're going to write it twice. So that is one expression. The other expression that you can have, a similar expression, if you use the first one. If you use the first equation, your A equilibrium would be exactly the same. It's going to be product concentration divided by reactant concentration. Your products in the first equation are H plus 1 and OH ions, and divide by the reactant concentration, which is water. So it's going to be H plus 1 concentration into OH ion concentration divided by the water concentration. Now, the thing is, last class, when I told you one thing, which is that water, whenever it's in large excess, remember, if you have a container full of water, so if liquid water, it's in large excess, its concentration is often taken as 1 or a constant. Because it will hardly vary. I mean, there's going to be so much water because I told you that the ions that are produced, okay, I told you that water ionizes very weakly. So even if I say that I have 10 moles of water in a container, there might just be 0.01 moles of HCO plus 1 and 0.01 moles of OH ions. So if the concentration of HCO plus 1 doubles, that means twice the amount got produced. There's some forward reaction. There would be very negligible change. But 0.01 से कितना हो जाएगा 0.02 if it doubles, right? A very tiny amount of change would happen in the concentration of water because water is in such large excess. So any reactant or product which is in large excess, especially water, its concentration is often considered to be a constant. So that means water over here is not going to be written in the expression. It's not going to be written in the expression. And therefore, or what you can write it as is that water's concentration is a constant. So you're going to combine it with this constant, which is your equilibrium constant. So the K equilibrium times the water concentration. What this simply means is, you don't get confused. Water's concentration is being taken as a constant. It's being taken as one. Or you what you can do is you can combine it with K equilibrium. You can do that as well. So just hold on one second. So you can combine this with K equilibrium. That's going to give you this. The expression itself is kind of irrelevant. All I need to do is I need to just get rid of the water in the expression. This thing over here is known as the water constant or the ionic product of water. That's known as Kw. Your expression now only remains H plus 1 times OHX. Or even if I pick the first one, it's going to give me the same expression. It's water. I'm taking that as a constant. I'm going to combine it with the other constant, which is this one. So my expression, if I use the first one, it would kind of be the same as well. It's just going to be H3O plus 1 times OH minus 1. Okay, both of these are exactly the same. There is absolutely no difference. There is absolutely no difference between the two. Okay, so is this part clear? Middle clear, Hala? Qasim, is this clear? Rumesa, is this clear?
Okay. Yes.
Okay. So remember, not I mean, just to keep it simple, the reason I just wrote this expression down was sometimes in the question they might say, okay, what does this mean? And this just means that it just means KW. Okay, so in very simple terms, KW is the ionic product of water. You have two equations which are basically the same equation. It's product concentration divided by reactant concentration. You just don't write this reactant in the expression. That's it. Same over here. Product concentration divided by reactant concentration. You don't write water because water is in large excess. Its concentration is going to be a constant. So you get this expression. So I'm going to just neatly write this down. So my KW is what? It's H plus 1 times OH minus 1, or if I, instead of using H plus 1, I write H3O plus 1. Okay, that is what KW is. Now, the other thing is that this KW has a certain value. As I'm, so that's our expression of KW. Both of the expressions mean exactly the same thing. Just for the sake of simplicity, I'm going to use from now on, I'm actually not going to use this equation. It just takes longer to write. I'm going to use this equation. So I've got water and it is going to ionize and it's going to form H plus 1 and it's going to form OH minus 1. So water would be ionizing. Now, what is the amount of ionization, especially if the temperature is room temperature? If it's 298 kelvins, which is 25 degrees centigrade. So at 298 kelvins, 25 degrees centigrade, if you have water, if you have pure water, distilled water, it will ionize very little and it will produce 1 into 10 to the power minus 7 mole per dm cube ions of H plus 1. And because OH and both of them are going to be produced in equal amount, it's going to have 1 times 10 power minus 7 mole per dm cube ions of OH ions. Okay, so imagine you've got pure glass of water, pure distilled water. It's got a lot of water in it. A small amount of it is going to ionize and it's going to produce this amount of H plus 1 and OH ions. So that's pure water at exactly 25 degrees centigrade, which is very less ionization. And also remember, if you increase temperature, the ionization increases. There's going to be more collisions and there's going to be more water molecules breaking down. तो यहाँ पे if you increase temperature, the ionization of water increases as well. So it's going to increase as well. So going back to this, you've got, I'm just going to write down the value of Kw. It was H plus 1 times OH minus 1. And remember, Kw is a constant. What is the concentration of H plus 1? That's 1 times 10 power minus 7. What is the concentration of OH ion? That's 1 times 10 power minus 7, right? So my value for Kw is going to be 1 times 10 power minus 14. And that value for all water that you have is going to be a constant. It doesn't really matter whether it's pure water or impure water. Remember, equilibrium constant does not change as long as you don't change temperature. As long as the temperature is 25 degrees centigrade, this value is not going to change. Okay, whether it's dirty water, whether it's pure water, whether it's your blood, this Kw is going to remain a constant forever as long as temperature is not changed, and it's going to have a unit. The unit is mole per dm cube times mole per dm cube. So that unit comes out to be mole squared and dm minus 6. So this is the unit that you're going to have for Kw. Okay, is this thing clear that the value clear? Is this clear what the value of Kw is? Hala, Binil, is this clear? Professor Qasim.
Yes, sir. Yes.
Okay, so Kw is going to remain a constant. Keep that in mind. Only temperature. So wherever you see water, Kw is going to have this value. Achha, but the thing is that the constant, the equilibrium constant is going to always have this value. Kw would always be 1 times 10 power minus 14. But this H plus 1 and this OH ion concentration, that doesn't remain constant always, because remember, if you have learned anything from equilibria, that is that the Kc remains constant, but the concentration of the reactants and products, it can change. But the ratio, because Kw was the ratio of the products and reactants, that does not change. So what happens is that your solution or the water that you have, you could have more H plus ions, but at the same time, the OH ions would go down. But the product of H plus 1 and OH ions, that would still come out to be 1 times 10 power minus 14. Okay, so I'm going to show you that. So H plus 1 times OH ions, that's what Kw is, right? So normally they're going to be equal 1 times in pure water. So if your solution is acidic, so for example, your H plus 1 concentration, let's say, goes up, and your H plus 1 concentration is now 10 power minus 1 mole per dm cube. That means your solution is very acidic. You have a lot more H plus ions. Your H plus 1 is going up. But if your solution is acidic and there's more H plus ions, the OH ions would drop. You're going to have a lot less OH ions, 10 power minus 13 mole per dm cube. There's going to be a lot less OH ions. But the product would still come out to be 1 times 10 power minus 14. Okay, so this is if your water becomes acidic. Okay, vice versa, if your water becomes basic. then in that case, your OH concentration might go up. Let's say 0.1 mole per dm cube, 10 power minus 1 mole per dm cube. But at the same time, if this water is basic, there's going to be very less H plus ions. So that concentration would decrease by a lot. But the product would still remain. The equilibrium constant or the water constant is still not going to change. Okay, so keep this in mind that Kw would remain constant. That will not change. In the water, the H percent could go up, but simultaneously the OH ions would come down, but the product would still remain exactly the same. If it's basic, the OH ions would go up, the H percent would come down, but the product would still remain exactly the same. So no matter how this equilibrium gets disturbed, as long as you don't change the temperature, the equilibrium constant is going to remain exactly the same. ठीक है? ये वाली भी clear है last चीज, is this clear? कि Kw does not change. Is that clear?
Yes.
बस ठीक है, ये कल कंटिन्यू करते हैं, ठीक है? With this enough, we'll continue tomorrow. Okay then. Office.